This afternoon we're going to start with Chris McDermott from Edinburgh, who's going to talk about another shale research programme which was launched sort of in parallel with the Shale X Environment programme, and give us some information from his perspective.
Thanks, Adrian. So I'm presenting on behalf of quite a large project, just as large as Shale X. So there's a couple of points where don't drill too deep on the questions because I'll start going red. I think I should also go red coming from Scotland, as we just banned shale gas last week. But I have this is being recorded, I've got to be careful here. I've got the impression that as soon as the English start making good money, then the Scots will get interested again. So the aspect I'm focusing on in this shale gas project is risk assessment, partly risk assessment. That's one of the core features of what we're looking at. And it's particularly making complex coupled process numerical models for risk assessment accessible to non-expert use. It's already a mouthful. I think many of you will have seen some of these numerical models which people put together. And one of the things we're trying to address is how do we make that available to a regulatory use, to an industry use, but also to a general public use. I'm going to show you what our concept is to do that, and I'm going to focus a little bit, we're going to bring the project towards the focus of what we call a risk-based corrective action interface, but I'm also going to introduce various aspects of the project. Oh dear, very small. I have to admit, it's so small, I can't even read it here. It's only this slide. So what's the objective? The objective of FRAC-RISK, just as Shale X's objective was in the end, is the assessment and reduction of the environmental impact of shale gas development. And we've got about 4 points which we highlight there. One of them is we look at 7 key shale gas basins across the EU. We collect data. From those shale gas basins. Actually, we probably do quite a bit of data mining as well. We have created modeling-based scenarios focused on 6 exemplary scenarios for the prediction of the migration of chemicals and other environmental impacts in the subsurface. We're trying to develop a framework for risk assessment, and we're looking for criteria for appropriate monitoring strategies. And at the end, as all of us are being encouraged to do, we're producing scientific recommendations, a knowledge base, and with the other 4 projects together, we're also going to be producing a common sort of best practices approach. So this gives you an overview of what FRAC-RISK is about. We start at the top, so this is the laser, with selected sites across Europe and the USA we've identified as locations where shale gas development is quite likely, or at least possible. We characterize those systems in a methodology which we call hydrogeochemical mechanical facies analysis. That's where we're looking at the characteristics of the subsurface in terms of architectural elements. In other words, we look at the subsurface as a series of building blocks. Those building blocks are defined by the process which we're looking at, which in this case is fracking of the subsurface and then migration of the fluids. And then the characteristics of those blocks may be permeability, maybe mechanics, but it gives us if you like, a Lego kit to reconstruct the subsurface, both in terms of characterizing the subsurface with our experiments, and also in terms of characterizing it for our numerical models and looking at uncertainty. So we've also got baseline data we collect, so we need to know what the change has been. And then we go through what we call the features, events, and processes risk assessment system. Now, FEPs are a standard procedure which come out of the nuclear industry. They're looking at all the various individual features of the subsurface. You put the subsurface back together and you try and identify what the most risky combinations are. Once you've got the most risky combinations in a risk register, you can then start developing models. You use those models, so we're going round here. You use those models to identify what a signal at a receptor could be. You look at mitigation and monitoring strategies. And then we look at risk reduction. In other words, do we need to monitor more in a certain area? What can we do about it? And then finally, all this is captured in knowledge-based scientific recommendations and legislation. Those red numbers there are our work packages, which follow that structure quite neatly. So I've got standing in the Geological Society, I had to put a slide related to geology into this, but we are very applied. These are the shale gas basins which we've been looking at, and it's very interesting to note that they're all in different settings, and they're all of quite different ages, geologically speaking. And so the geomechanical FACES approach is a methodology which helps us to compare what's happening in one area with another area, what are the common themes, what are the common features, what are the driving forces, and what can we take out of that to help us identify which areas are going to have which problems. The underlying principle behind this work is a common one used in hydrogeology for contamination assessment, and you'll notice in the recent NERC call that it's also a fundamental concept which they're now deciding to apply, and that is the source pathway target approach. So in terms of fracking, we've got multiple sources down here, which in principle release something nasty, and somehow that nastiness has got to make its way to the surface, either through the well casing, through various pathways, through faults, some other way. It makes its way to the surface where it impacts multiple receptors. And so we map that onto a risk-based corrective action approach where we subdivide the surface now into underburden, reservoir, overburden, aquifer, surface environment, air quality, various compartments which will be impacted, or there's a pathway through, or something is released. Now, frac risk, as I mentioned, frac risk focuses on 6 exemplary modeling scenarios. These scenarios have been selected according to the processes operating. Now, by processes, I mean what are the thermal, hydraulic, mechanical, or chemistry processes which are operating, coming out of the sort of coupled process literature and understanding. So we've got geomechanics of frac development, we've got hydromechanics and geoseismicity, we've got various different driving forces, either the pressure gradient due to injection or some sort of capillarity or diffusion. We've got time scale in our scenarios, 2 hours for the fracking process itself, up to 100 plus years for methane migration. We've got spatial scale, near field and far field, and the different fluids involved. So it's becoming a really interesting system to start playing around with. If you have a slightly closer look at the modeling scenarios which frac risk are focusing on, we're looking at regional fluid flow. What's the diffuse background? What's the natural background? We're looking at fluid flow if you've got a fracked source. We're looking at rapid transport through faults or abandoned wells, so legacy structures. We've got chemical transport. We've got pressure migration and fluid flow. And we've got the microseismics in the system there. Now, I'm presenting some modeling work, but it's also worth mentioning that to validate our models, we do have experimental baseline data. We've got, this is an example of some data which we're producing on fracking itself, where we take a sample and we actually frack it. You can see here the size of the sample we're using. So this is a normal 5 centimeter core sample, and this is now 20 centimeters by 20 centimeters. It's been fracked. You can actually see the frack there. We can put it in a special device to look at the properties of the fracture under a changing stress field. And this gives us data to validate our models. We've also got other types of work. So here we are looking at what comes out of the formation in terms of geochemistry, pressurization, in situ reservoir conditions, and looking at the change. Can we predict if we put a certain mixture into a formation, can we predict the geochemistry coming out of the formation? And that's coupled with understanding a lot about what's available in terms of the literature. So what are the major challenges I've mentioned here? Multiple geological settings, multiple numerical analytical models, trying to manage and express uncertainty, trying to combine the results to be usable by a wider audience, devolved legislation. That's a little bit beyond what I'm going to present here, but in the EU, you've got all sorts of you've got national legislation and you've got local legislation. And one of the barriers is, of course, social license and mistrust. I'm going to be looking at the sort of top 4 challenges there in more detail. Now, we're trying to express our risks and our top-down and bottom-up combinations of hazard assessment in terms of a bow tie diagram. This is the bow tie diagram approach. This is the nasty thing here, which happens. This is the thing which you are told is where you lose control of the system. Something happens unexpected. Now, before that happens, a threat has to have been present. The threats are defined by the risk register, the features, events, and processes risk register. And there are various ways, if a threat is building up, that you can prevent it from occurring. Threats are for instance, injection procedure or pressure monitoring can make you aware that a certain FEP, a high-risk FEP, is in danger of being triggered. If it does happen, then there's going to be a consequence at the surface. Maybe there's pollution, maybe there's transport, but there are still a number of steps before you actually get to this impact, and this is the period of recovery where you can have leak detection systems, you might have isolation valves, maybe something you can do, maybe something you need to monitor or to measure. Now, we try and express our risk assessment in terms of the RCBA platform. And the idea behind this is that there are 3 levels of assessment. The lowest level of assessment is the tier 1. So that's the question we ask there is what combination of geology and operation is going to give us trouble? So there you see we've got our geomechanical facies characterization, our FEP ranking, and various other baseline data sets to look at. So when we have identified what's going to cause us trouble, we then go to our generic models, put the information together, and try and predict what's the transport from the source of trouble through to the receptor of trouble. And that's where our modeling comes into play. So we've done our level 1 assessment. We've identified our threats, and we now map the threats to various different modeling scenarios. Now, these models are very complex. You've got several parameters, you've got several processes operating, and you want a system which a general user can assess. In other words, there's no use putting everything together in some sort of platform, pressing the button, and you get that Windows thing rotating around and saying, please come back in 2 weeks' time, and please don't switch your computer off either in 2 weeks while it calculates what's going on. Some of these models can take weeks to run. So what FracRisk's come up with is a way of gluing this type of assessment into an RCBA platform by using what we call a response surface or an expansion of polynomial chaos functions. I'll show you what that is now. So what we try and identify for our Tier 2 assessment is a standard range of parameters which each generic scenario has, and additional parameters which are specific to that assessment. And we use our computer models now to predict our response surface. Now you have to realize that a response surface could take several thousand computer simulations, because we're trying to capture in that the uncertainty as well as the expected outcome of what's going on. So let me show you pictorially what's going on, because I realize if you're like me, I look at these things and I don't get it until I see some pictures and can relate to it. So if I've got a numerical model of a problem, I then predict an area which is going to exceed threshold value determined by some sort of chemical database. So this could be the XY, the planar distribution of a contaminant due to some event here. And what I see is this red area is a problem. Now, this has been evaluated by computer programs, and we've taken maybe 4 weeks of intensive work to come up with this surface. What we do is we fit that surface with a bunch of polynomial functions based upon our generic parameter sets, and it's these polynomial functions, this function, which we export to our risk-based corrective action. And what it means is it takes a few seconds at the most to come up with the uncertainty and the prediction of what's going on, rather than come back in 2 weeks and don't switch me off. So there's a workflow model for understanding what the various sensitivities are. I'm not going to dwell in this, other than maybe here, if you can just see here, you input a parameter set, you run the full set of model, you construct your surrogate model, you compare that with some values to validate it, and when you've got it, then this is your result which you're exporting. This is an example of one of those surrogate models. We've got some sort of fracturing going on here. We've got fluid injection. We've got standard parameters which we can play around with, and then we get standard outputs at the surface, which we then fit with our surrogate model. So the last couple of slides, the risk-based tool. This now becomes a platform where the general public can press a few buttons and say, I've got this geology, I've got this fracking going on, what are the key risks which we need to watch out for? So it becomes this interactive tool which we were hearing about before, where instead of just showing or telling, we're into the engagement. We integrate relevant geology, relevant properties. We can build conceptual model of risk relevant to different sites. We've got pathway receptor pairs, we've got health risks, we've got chemistry in there. So a couple of slides to show you how it could look like, or how it does look like. You can select an area, you can select where your fracking will be taking place, you can select a geology, and then once you've put your geology together, from some sort of drop-down list, you can select different chemical parameters, different things which are going on, and then in the end you can run and have an expression of the risk. So this is a tool which people can use interactively to work out what the key issues are. Okay, so that's the concept of FracRisk. That's where we're going. That's what we've been putting together. So the expected impact is hopefully we reduce the uncertainty in fracking. Hopefully we give engagement to some people. I'm sure we'll get a few teenagers who can break it within seconds. But actually I should put my own family on that first. We provide an understandable, ready-to-use platform for risk analysis. We hope that will contribute to the formulation of regulations, and of course a more rational approach to site certification, and also maybe possibly allowing Scotland to frack in the future, but we will wait and see on that one. Okay, thanks very much, Adrian.
Thank you, Chris. Any questions?
Richard.
So is this going to be kind of public available? i.e. you're going to put this risk register, type in your formation thing on the web for people to have a go at?
Yeah, I mean, that's the aim.
Yeah.
The various building blocks are already publicly available in terms of the risk register. And actually in November, we're having the first trial workshop of it in Barcelona, in Catalonia. It's also interesting. So, and hopefully by the end of the project, we will have demonstrated the use of this for a couple of scenarios. To be strictly honest with you, I doubt we're going to be able to cover all the scenarios, because there was a lot of thinking, a lot of intellectual property involved. Well, not property, but just the development in how we're going to get from this complex system with the different geologies to something which is easily expressible.
Yeah. So with the information that's collected, obviously there's going to be a feedback loop. Obviously people then go in and use your system and come up with some answers, and they're going to have questions and everything. So how does then that all get translated into what effectively might go into some kind of regulatory or planning type of applications?
So I think this will be making people aware of what the key issues are, which they should be looking at. In terms of what's going on into the regulatory or planning or legislation type level, that's a different document, really. And that's a document which the 4 projects are working on together.
So, sorry, the next point I had is, how are you going to calibrate you've got European basin scenarios set up there with no frack activity in them.
Yeah.
So how then are you going to calibrate these models to real life, which will be different from some model scenario? We know that's generally the case.
Yeah. I mean, we're using models of different processes which have been benchmarked, which, and they're it's out there in the literature that, if you've got chemical transport, how do you deal with it? Right. But obviously it's going to be different for a specific site, and you can always say heterogeneity is always going to be an issue. But I think what this will do, hopefully, is make people aware this is what's going to happen, and these are the parameters which need to be monitored. And that's the feedback now to the next stage, which makes it more, or reduces the risk, potentially. Okay, thanks.
Strong. So, next speaker, Niels Blackburn. Going to talk to us about measuring permeability and tortuosity in shales. And Niels worked with a while, very productively.
Yeah. Well, yeah. Thanks for having me back here, Adrian.
You fooled us into thinking it was productive.
And we're hoping something comes out of it. Yeah, thanks for having me back, everyone. My name's Niels. I was working with SXT over the past year and a half nearly, playing with some samples from Halliburton and sticking them in Tom's lab, doing some permeability measurements, and then trying to understand if we can identify or characterize that directional permeability by looking at the 3-dimensional volumes of these samples. So we're going to talk about the tortuosity, the parameter of tortuosity within shales, and that's actually a fundamental parameter that we can use to quantify directional permeability or relative directional permeability. So bear with me as I get myself back into shales. When I started, I got hooked on this graph because I thought there's actually a lot of information in here. So before I actually get onto this question that's listed on top of the slide, maybe the first question should be, why do we need to understand the permeability of shales better, considering that when we're extracting the shale gas or the gas from our reservoirs, is we're changing the permeability structure by fracking it, by fracturing up the rock to change the permeability and increase permeability and suck out the resource. And the answer to that, I think, is in this question here: where is the recoverable shale gas? So what this graph here is showing you is, well, normalized to initial stimulation of a well, we get a high rate of recovery of gas coming from the well. And with time, that rate is considered, this is in months at the bottom, so these are wells from 2008 to 2013. All we're seeing here is better know-how of how to extract shale gas. That's why we're getting a lot more out in later years. But there's a lot of gas left behind that is coming out of these existing or stimulated reservoirs. And people have looked at this decline curve, so this decreasing rate, in terms of the interconnectivity of fractures at depth. Right? So there's a comment that the horizontal wells have an unbounded vertical reservoir based on interconnected fractures. You heard Phil Meredith talk about what the fracture systems might look like at depth. So the concept there is that gas is actually coming from further away to get to the well. And I'm putting out the question, is that necessarily the case? When we're looking at shale gas systems or shales, we're dealing with a hierarchical permeability structure. We're starting off with our well that goes down to the reservoir, a nice big open pipe. Then we're stimulating the rocks by inducing fractures and putting little proppants in those fractures to keep these open. So again, we're going down in permeability. So K2 is its lower permeability rate than we have in K1. And these fractures, or this induced network here, is interconnected to an existing natural fracture network, induced fractures at depth, with your next permeability structure. And then around that, we get what's related in the shales. And you can see in this figure B here, sort of this mottled background. This is from results from the study of the samples we looked at. This is the distribution of porous phases, or of porosity and kerogen in the samples. So at the scales of a few millimeters already, if you're punching fractures through, unless we're actually pulverizing the rock, the distribution of your resource is still going to be quite diffuse. So the long term, or the longevity of the recovery out of these rocks is going to be affected by the permeability in those shells around your fractures. So we're going to have a look at this in a little bit more detail now. And when we talk about shales, anisotropy is a term that we're all happy to deal with. We know shales are well-layered rocks. You can consider flowing along them is a lot easier than flowing across them. These are all well-known concepts of shales. So here are two samples. We had a whole sample set that we prepared lamination parallel cores. So you can see here's the bedding lamination, tiny little picture, but here's a schematic of it. So the laminations of the shell, and here's one cut perpendicular. And we put them in the lab at UCL to measure the permeability using argon gas and also water. And what we get is about a 1 to 2 order of magnitude flow difference in bedding parallel flow and bedding perpendicular flow. So this is exactly the numbers that you see in the published literature. So we're in that sort of range. Interestingly, we see water and argon gives you the same results. So there's really a fundamental geometry related to the rock that is defining this permeability. One of these samples here, just to explain the rest of this figure, this sample actually cracked naturally, so then we had a little open fracture. We put this back into the sample, and you can see the permeability increased a little bit. So for the shells itself, we're talking about the nanodarcy range, and when it comes to cross-bedding flow, we're getting down into the sub-1 nanodarcy flow regime. And here we just try to simulate what happens with depth by increasing the effective pressure on the sample. But we'll leave that for now and just focus on this anisotropy. And like I said, there's a fundamental geometry within these samples that's defining what those fluid pathways are. We're getting this 1 to 2 order of magnitude of flow difference, anisotropy, in most systems that we're looking at. So can we start to image these interconnected pathways? So just to start off, we put a few thin sections into the ChemScan to have a look at the mineralogy and the mineral distribution. It's a nice green picture, essentially showing us shales as a clay-rich sample we're looking at. These are about 60 to 70% clays. And a nice distribution of clastic grains, quartz, feldspar. The ChemScan also pushes out porosity plus organic carbon content, so essentially holes or zones where it didn't see a mineral. This is probably an underestimate because this is done on a point count on the sample. So if you happen to hit the edge of a mineral, you'll get that mineral in case of that. But nevertheless, if we strip away the rest of the volume, we get this distribution of pore space or pore space and kerogen. And you can see here already at this scale, you can pick up a nice bedding parallel fracture, but there's a really diffuse, in a sense, even though this is a stochastic environment, it's a homogeneous distribution at the scale of, or here's 100 microns. Across the millimeter scale, it's a homogeneous distribution of pore space. But the other thing you can see is the interconnectivity in 2 dimensions is next to nothing. You can probably get a few pieces up to about 40 microns together. And to consider most of these fractures, if they are proper fractures and not kerogen seams, are going to be closed at depth. So in order to understand the interconnectivity of these permeable phases, to try and understand what are the available pathways at depth, we looked at this in 3 dimensions. Now, this is work I did with Francesco. He's sitting I nearly pointed the layers at you, sorry. So we prepared two pillars, one about 2 millimeters, and down here is a little 64 micron pillar. We had a look at those at the XJCT at the Electrochemical Innovations Lab. And you can see here nicely, at the scale of a few millimeters, we can already see compositional layering in the sample. So we get a slightly more clay-rich layer and a slightly more silt-rich layer. Here's a fracture coming through the little bit of the silty zone. Again, these are probably closed at depth, but I'm starting to pick them out quite nicely in here. And what I want you to take away from here already is the alignment. Well, let's start with this. The darker colors is all clays. These sort of moderate grays are quartz, feldspars, and carbonates. And white is pyrite, comes out quite nicely. And then the darker zones, this is our porous volume, so it's porosity and kerogen. We weren't able to distinguish the two at this resolution. But what's important is the alignment of those is already replicating the fabric of the rock. And the same, if we go over to this, is it possible to turn this down a bit more, the lights? Evgenia? Oh, there. Sorry, upstairs. There we go. As you see here, potentially, there we go. You can see a few clastic grains in here, and you can clearly see the clays wrapping around those grains. So after it spins past this, here's some nice pyrites. But here you got some clays, they're wrapping around these clastic minerals. So at the nanoscale, you're seeing that the rock fabric that we see at the macroscale exists all the way down to the nanoscale. So this whole thing is 64 microns across, and the resolution here is about 126 nanometers. So it is really this rock fabric defined by the clays that exists through the entire scale length. And that is what's going to define your interconnectivity of available pathways or whatever kerogen and porosity is available through the sample. So we can have a look at that. Again, so we've segmented out the different phases, and we're talking about 60 to 70% clays. So clays are really the dominant minerals in this rock, and they're defining the overall rock texture. And in red here, we get the pore volume. Again, just to reemphasize, we're including here pores and kerogen in this volume. So these are the available permeable phases for gas to migrate through by one or another mechanism. Similarly to the ChemScan, we can strip away the rest of the volume. I've left pyrite in here in green, which is to give a little bit of a spatial or depth perception of the samples. This is rotated around. And the red is all your porous phase volume. And it's much nicer here, but it's okay. Again, the point here is that the rock fabric is replicated by the porous volume. So the distribution of the porous phase follows that of the rock volumes. You can see quite nicely these anastomosing, wavy layers of interconnected porous phases. That fracture that we saw, that comes out quite nicely here, sitting in the silty layer. So that's fine. It's also quite wavy. Fractures are never exactly straight, but again, the clays are really a defining factor in the geometry. The same is the case at the nanoscale. So here you've got 5 microns for a scale bar, and you can imagine in this void space over here is a nice quartz grain or a plagioclase. I think we were able to see some lamellae twinning in there, so I think that was a plagioclase. But you can see again at this scale that your clays are really forming what the pore space distribution is going to look like at the scale. And now looking at this image, if you want to try and imagine to move through these pore spaces, so through the red volume from left to right should be relatively simple. There are quite a few gaps already. But if you want to go from the top to bottom, you really have to, go in and out of the slide, up and down, left and right, using everything available. So there's a lot less opportunity to move in the different orientations because of this inherited geometry. So we used a program called Tar Factor by Cooper and his group to try and quantify these permeable pathways, so the interconnectivity of the pathways. So here's a schematic of how this works. We started on one side of the volume. This is, again, just porous volume, so in black. And then progressively, the program tries to simulate pathways, interconnected pathways through the sample, taking into account the geometry of that pathway. So it actually measures a tortuosity factor, which for purpose of this talk is about the same thing as tortuosity. Essentially measuring the length that gas would have to travel through the pore spaces to get to the other side. And the length will increase based on the convolutions that it needs to pass through. So at the macro scale, or the micro CT scale, macro relative terms here, so if you're looking at the lamination parallel flow, there are lots of pathways that this program can find out, lots of interconnected pathways through the sample, and they're relatively straightforward. Conversely, if we want to go across the sample, this starts to look a lot more intricate. There's a lot less interconnectivity through the sample, especially, for example, if you focus on this little zone here, there's only 1, 2, 3, 4, 5, or 6 or 7 nodes across 0.5 millimeter of it. So without those nodes of interconnective pathways, you won't find flow through this portion of the sample. But nevertheless, you can get these nice convoluted pathways. You can line these out with a string, and you can start to imagine what the difference is in length. The same again at the nanoscale. What's quite interesting in flow along bedding is that even the parallel flow starts to become more convoluted. And you can imagine that with the original, with these clastic grains, these quartz grains lying there, and the clays wrapping around those. It's not really a straight line. There are also nice convolutions involved in that. We were lucky enough to happen to have this node in the sample. If we had stopped our image over here, then we wouldn't have been able to model this flux through the sample. But again, you can see trying to get from top to bottom through the sample is a lot more difficult than going along it. Okay, so Tar Factor puts numbers on this, and here we are on the left. We have in solid lines as our lamination parallel flow, so long bedding. And in dashed line, that is lamination perpendicular flow. So this is the tortuosity factor, in essence, the length parameter across the sample or through the sample. And you can see what's coming out quite nicely is an order to 2 order of magnitude difference in the magnitude of the tortuosity factor here. Right, this is the same at the nanoscale as well as at the nano CT and the micro CT, so across these lengths. So the further you need to travel through the sample, the more convoluted, the more tortuous, or the longer your pathway becomes. Just for comparison, here's that silt-rich layer, that fracture that we saw. It's a much straighter pathway through the sample. So this is what we're doing when we're fracturing the samples. We're creating fractures, easy pathways, straight direction, get the gas out. So it's really the tortuosity factor. So if you look at the effective flow, this equation here is what this program using Tar Factors, the effective diffusivity is representative of the diffusive flow through a porous media. In this case, we're averaging out Darcy flow through pores and diffusive flow through kerogen. But the epsilon here is the volume distribution of that. We've shown is somewhat homogeneous depending on the system that you're looking at. So within shales, where you're looking at micron scale minerals, this scale is actually adequate to characterize a volume percent of 60% clays. So that the geometry is really fundamentally, or the permeability and isotropy, there's too many long words in there, is defined by tortuosity factor. So if we can quantify tortuosity factor, we have a variable that actually measures the directional permeability relative to one another. What we also did just on a side is we changed the volume proportion of the porous media in our samples, just manually changing the grayscale threshold to increase or decrease that red volume in the sample. And you could see if when we doubled the volume to 20%, the tortuosity decreased. This means there were more available pathways and they were much more direct to get across. This is conceptually quite neat. I think a simple thought to put forward is if there are more available pathways available in the rock, it's easier to travel through. And similarly, if we decrease the volume to 5%, we couldn't get further than maybe 14 microns through the sample. And this is lamination parallels. This is a long bedding. And at 3%, we couldn't even migrate further than 10 microns through the sample. So maybe this is showing us something that a threshold, a critical threshold of porous volume that's required for gas to actually be able to migrate through a shale. So, how does this fit into the whole story? Again, so we've punched the fractures into these shales, and the greater reservoir that's accessed, right in the beginning, you're getting the immediately accessible fracture-captured gas. So all the gas that's right next to these fractures is getting sucked out and interconnected via a broader fracture network, which is giving us this main peak in shale gas recovery. The longevity of these systems is actually defined by the geometry or by the mineralogy of the shales around it. Now, because of the nature of clays and the anisotropy of clays, and the fact that we can see that K5 here, the vertical permeability, is orders of magnitude lower than parallel to permeability, it's really that the broader nature of this fracture reservoir is probably related to a lateral extent around the fractures. Rather than being interconnected fractures from much further away, it might be within the same reservoir volume, but just along much more convoluted pathways and difficult pathways to travel through. So that's it for me. I'll leave it there. Thank you. There we go.
Any questions for you?
Cool. Yeah.
This might be a sort of silly question, but you said there's more interconnectivity that's sort of laterally than vertically or whatever. And in some earlier talk, I think it was Phil was saying that you want to sort of avoid, I know this is very small scale, but you said it goes all the way up to big scale, but you want to avoid sort of horizontal fractures because they can intersect with faults or whatever. But in what you're talking about, isn't it more likely that any fractures are going to sort of go along interconnected pathways and make horizontal fractures more likely? I don't know.
So that's a very good point. So the problem with taking a shale at surface and trying to fracture it, it will break along the laminations 9 out of 10, well, 99.999 out of 10 times. Right, so that is a problem. But what we're really looking at is just the porosity distribution of the sample. So once your fracture network is induced, then the accessibility of gas within your reservoir to those fractures is going to be predominantly horizontal. Now, I think with Phil's talk, you were talking about developing fractures at depth. You've got your confining pressure that will help you develop your vertical fractures. So I think if you talk to a lot of the fracking specialists, one of the problems is a lot of these fractures migrating parallel to bedding. And to try and overcome that by understanding your local stress regime, which direction you want to drill and then frack, so that you don't create horizontal fractures. But once those fractures are then in place, we need to understand where this gas is coming from. So we're talking about, okay, what is actually being missed? Essentially, what I'm trying to say is that even though we're getting a lot of gas out, there's still a lot of gas stuck within the, I'm not going to say immediate vicinity, but within close proximity. And that is coming out slowly because of the way of the permeability structure. And we can't pulverize these rocks because then we're into a whole new rheological system and we might all sink a little bit. I don't know. That's beyond my comment. Yeah.
Okay, thank you.
All right, thanks.
Next speaker, Don Westercott from Halliburton, via Columbia.
Thank you, Adrian.
Going to talk about core vault technology for high pressure coring.
Thank you. Thank you, Niles.
Of gas produced. This whole sequence that we're doing in the lab is focused on measuring 3 fundamental parameters: pressure, volume, and mass. pressure, volume, and mass of the gas that's coming out, pressure, volume, and mass of the fluids that are coming out, and mass and volume of the rock. And by putting pressure, volume, and mass together, we're able to, with calculations, we're able to determine fundamental reservoir parameters. We're actually doing a mini DST, a closed chamber DST of the reservoir. We've got approximately 650 cc's of rock volume. We've got the annular volume of this pressure vessel is nominally 952 cc's.
Good afternoon. It's an honor and a pleasure to speak to you this afternoon on an important topic, energy. I'm Don Westacott. I'm the Chief Advisor for Unconventional Reservoirs, Halliburton. Energy is important. Energy has always been important. Prehistoric man harnessed fire. It gave him warmth, shelter, light in the darkness, protected him from animals, predators. Today, energy is as important today as it was back in prehistoric times. It's fundamental to the prosperity of humanity. We talked about earlier in the first opening slide by Alberto about two words, challenges and opportunities. And I would like to carry on that theme about challenges and opportunities in our energy sector. We strive to do three things in the energy sector, just three things. To produce energy reliably, to produce energy economically, and to produce energy safely. Just three things. Now, just before lunch, Jill Cooper showed how her company, Anadarko Petroleum Corporation, looked at those challenges, those many challenges that we are faced in the energy sector today. And through her company's leadership, has acknowledged them, addressed them, and is now mitigating those multitude of challenges. It's all about security of supply, responsibility, sustainability, and prosperity to all the individuals on this planet. Now, in addressing those challenges and opportunities currently, in the recent past, in the last several years, our industry has been faced with ever-increasing challenges. Some may say those are bigger than challenges. It's a crisis in our industry. Now, the word crisis in the oil and gas sector is not new. I want to remind us, everyone here, that crisis has been used before. In fact, nearly 75 years ago, King Hubert indicated through his modeling, some of us with a little bit different gray hair color can remember this, that we were going to go through a crisis. On or about the year 2000, we would have a shortage of energy on this planet. This was the model, established model. And that would result in power blackouts, escalating costs of energy, particularly oil and natural gas. Let's test that model. Here we're in 2017, well past the peak date of peak oil. Where are we today? And let's test that model against U.S. oil production today. Here it is. And true enough to King Hubert's model, peak oil in the U.S. peaked exactly where it said it is. Each basin, each reservoir, each geological area or country would peak at a slightly different time. But for the U.S., that peak was predicted to be about approximately 1975. And sure enough, oil production in the U.S. did peak in 1975. It had a short or a reprieve in the early 80s. All remember what that was. Prudhoe Bay came online, major discovery Alaska. And then we have experienced in the United States a decline of domestic oil production for the last 20 plus years. Something happened. A complete reversal, a complete turnaround. Magic. Never in the history of the oil and gas sector has such a dramatic change in domestic production happened in our industry, anywhere. How did it happen? 2 words: unconventional reservoirs. One being the organic rich mudstones, the so-called shale plays. I dislike that word. Shale is not a good terminology for what we're dealing with here, but it's like the people in New York understand 1 or 2 syllables, so we call it shale. And here's an indication of what has happened. What is that dramatic turnaround in domestic oil and natural gas production? In the last 12 years, the United States alone has increased domestic oil production and gas production over 12 million barrels equivalent. A dramatic and stunning turnaround. How did we do it? What was the success factors? What made it happen? In 40 years, working in the oil and gas industry, in 40 years, working unconventional reservoirs, I've only discovered one way of doing it. And we saw many of examples of that here this morning and today. Look at data. That's the only way that I know how to reliably, cost-effectively, and safely develop hydrocarbons, oil and natural gas. Many types of data, and we've discussed some of those types of data today. Here's the short list, and I draw your attention to that bottom line and more. An integrated approach that takes a wide range of disciplines. In exploring for unconventional reservoirs for the last 40 years, I wanted to do something better. Our industry wanted to do something better. It's my honor to present a technology, very briefly here this afternoon, that addresses some of those data requirements, shown in red. We've called that technology Corval. To attain information. Dr. McDermott, I acknowledge your first slide, where you stated, we want to have cost-effective data requirements to increase certainty, and I'm going to add 2 words, and reduce risk. And this technology objective is to do precisely that, increase certainty and reduce risk. Now, how do we do that? How do we do it? We don't operate in a vacuum. We work very, very closely with our industry partners, with our clients and other service companies. We go into the subsurface and we obtain reliably, quickly, and safely subsurface rock samples through a wireline conveyance. We place those precious core samples in a downhole specifically designed container at 20,000 pounds pressure and 400 degrees Fahrenheit rating. And then we do something new. At a command from surface, we seal in the reservoir. We now have the rocks, but importantly, we now have the fluids, those precious hydrocarbons in the rock. And we bring those pressured samples back to surface reliably, safely, and efficiently for detailed laboratory analysis. For the first time, we have the entire genie in the bottle. This is the technology. We are addressing organic rich mudstones, these so-called shale plays. You know how I feel about that word. But we're also looking at mature fields in the Middle East, in North America. We're looking at unconventional reservoirs. We're looking at gas-oil ratios and liquid-rich plays. And we're looking at the very, very properties that you've heard about today and more. Ronnie, absorbed gas, deabsorbed gas will be speaking about that in a few minutes. But we're doing more. We've advanced the technology in the last 6 months. We are capturing the rocks. We're capturing the fluids, the hydrocarbons, the precious commodity in the rock. And now we've advanced the technologies to measure pressures by putting smart sensors in the tool. But we've done more than that. We've modified the tool. We've increased the amount of cores. We've looked at a special compensation system that puts the chamber into an isochoric state in the laboratory so we can conduct detailed pressure, volume, and temperature, PVT analysis and equation of state modeling without removing the reservoir rocks. Here's a picture, a diagram of the instrumentation. But we've done more than that. We've enhanced the technology to include a specifically designed exclusion fluid, 1 liter of fluid, just like this bottle here, that's placed in the pressure vessel before entering the wellbore, that's inert, that's non-miscible with both the hydrocarbons and the water and the drilling mud, that is reservoir rock compatible, that's HSC compliant, and is non-hydrogen based. For the first time in our industry, in the oil and gas coring industry, we can bring back uncontaminated samples without the contributions and contaminations of the drilling mud. Many of the wells that we drill, our industry drills, are oil-based mud, completely contaminating the samples, the very hydrocarbons that are in the rock reservoir. Here's an example. I was recently over in Kuwait, in the Middle East, running the operation. This well was a 10,000-foot well drilled with oil-based mud. I can't bring a sample into the room, but oil is great, but unless you have it around you, that completely contaminates the sample. It's black. We went into the wellbore, cut our cores, sealed it, brought it back to surface. This is a photograph that I took in the laboratory of emptying the pressure vessel. The results are clear. Crystal clear. Elimination of the drilling mud contamination means that the reservoir fluid properties that we are investigating for our industry are pure, are correct, are valid. This is the technology. And we're very, very pleased to develop that. We've installed smart sensors in the downhole technology so that we can measure pressures and temperatures and times, and that it gives us critical and important reservoir evaluations technologies during the well site operations all the way back to the laboratory. Let's stop for a moment and actually look at some data. Now, Niles, you talked about the Marcellus. So I think I'm going to carry on your theme, and I'm going to talk about the Marcellus. In this case, we're all going to get on our smartphones, go to the web, and look at gas in place numbers that have been published for the Marcellus organic rich mudstone, the Marcellus shale in Appalachia. This work, Roddy, is through canister gas deabsorption work, the same technology that's been migrated over from the United States Bureau of Mines, where 3 fundamental properties are reported: residual gas, measured gas in the lab, and lost gas. And lost gas, just to remind ourselves, is gas that is lost from our core, our cuttings, our samples, before the experiment is conducted in the laboratory. This data, this published data for 150 rock samples through a wide range of Marcellus wells in Appalachia, estimates between 50 and 75% or more of the total hydrocarbon, the total gas in the Marcellus, is lost before the laboratory experiment commences. Now that's like having a 75% tax rate. Even back home in Canada, the taxes aren't that high, but heavens, I wouldn't like it. My wife would even like it less, but nevertheless, our industry has come up with an estimated total gas in place, which includes the lost gas that escapes the samples before we get them into the deabsorption canisters, a mean of 78.2, standard cubic feet per ton. Our industry is basing the economic development of the Marcellus Shale based on this data. Now let's go back. Let's go back to the Marcellus. This is our first well that we've ever did with the technology, and do one thing different. Let's use the Halliburton Corval technology and go back and drill an offset well to that same reservoir, to that same shale, and this time have 0 lost gas. Here are those results. We told our clients and we told our industry that the volumes of gas in the Marcellus Shale are now 2.5 times the previous estimate. I told our executive, you know, that's like telling each one of you that your salary just went up 2.5 times. I also made the comment, I'm guilty of this, if that doesn't make you excited, you're probably getting paid too much. And I still have a job, but they seem to not appreciate the humor in that remark. I don't know why. But nevertheless, this was important data in the reservoir assessment, the development program, and the economics of these organic rich mudstones, of these shale plays. And we're doing more, much more. This was our first process out of the box 3 years ago. And we are delighted to move this technology forward. We see a direct relationship between pressures, volumes, temperatures, and ultimate well productivity of the measurements that we're making both in the laboratory and downhole. And we're excited about a wide range of measurements. And you heard some of these today: geomechanics, fracture propagation, compositional analysis of the produced hydrocarbons. You know, it's all about the fluids. Today in the U.S., with the shift of liquid-rich shale plays, we are going into the subsurface safely, reliably, economically, and sampling level by level, zone by zone, and sampling those critical fluid properties before hydraulic stimulation, those massive, expensive frac jobs are executed, and targeting specific intervals. Here's an example from the Permian Basin. 6 individual reservoirs, stacked reservoirs, where we went in and sampled zone by zone and did quantitative API, gravity, oil properties, oil composition, and it's colored, the colors of the rainbow shown in depth. And this is critical information. It's the only way to extract fluids out of this rock previously is drill a horizontal well for a mile and a half and do a $8 to $10 million stimulation. And to do that 6 times is cost prohibitive. Here we're doing that quickly and then analyzing the results in a week and turning around and say, okay, drill here, don't drill here. Fluids, pressures, compositions, rock quality, geomechanics, those factors are critical in reducing risk and driving economics. We're working, and it is our great honor to work with UCL, Adrian and his whole team, of advancing this technology forward and working with you. And it's been my great opportunity, and I want to thank you all for having the opportunity to speak and share some of these advancements here with you this afternoon. Thank you. Okay. Questions? Oh, and don't be afraid at shouting at me. My ears are still a little bit plugged from the jet travel. Please.
You go first.
Thank you so much. And at the beginning, you mentioned the crisis we're experiencing now, the industry. So, it is well known that mainly this is due to the politic games. However, my question is, would you say that we are, as specialists and engineers, are able to solve the situation, or we just have to wait till the moment everything is solved on the government level?
Well, let me see if I understand your question or can give you a succinct answer. as engineers, as geoscientists, as geologists, as exploration,
Use the microphone.
we're still learning what we don't know. And so reinterpretation, as we get more data in, is just a fact of life as we continue to learn. And I think whether you're my age, you know, your age, we're still learning about these unconventional reservoirs and the technologies and techniques that give us an opportunity to do three things well. Thank you.
Thank you.
Chris?
You're talking about Hubert and his sort of peak oil. You're talking about Hubert and his peak oil sort of prediction. Was he factoring unconventional resources into account when he made that at the time?
I think it's clear that King Hubert did not see unconventional reservoirs on his radar screen when he made his models and he made his predictions. So the answer is no. I wanted to with no disrespect, King Hubert was a great and eminent scientist, and he would have been absolutely correct on. In fact, if you look at Norway today, and Norway's oil production, I'm not picking on Norway, I'm just showing an example. The King Hubert's model and actual oil production from the country of Norway are spot on. I don't have that to support that. I'm here, I'm sorry, but if we look at that data, so, and you're right, Norway currently has not got an active unconventional program, so King was right. He just didn't see the resource potential in these shale plays, so-called shale plays. Thank you.
It's a quick question, Chris.
Yes, I'm going to throw you a wild card. What does Halliburton think about methane hydrate production?
Oh, I mean, I can only give you my personal answer that methane hydrate production in the future, and I can't give you a time frame, has the potential to be much, much larger than any shale play on this planet. That is my belief. Now, whether that will happen in my lifetime, I can't say, but there is a huge resource potential. You know, one thing about you people here, we're great problem solvers. And what has made the U.S. shale play work is great problem solvers and great working together to solve problems at all levels. Oil and gas sector, the service companies, state and local governments, and special interest groups, all working together to do those three things. Can I end it there?
Thanks.
Thank you.
Thank you very much.
Thank you.
Next we have Gary Edwards, going to talk about guidelines for environmental monitoring.
Okay, thank you, Adrian, and thank you for the invite to come along and talk today. We've had some fantastic presentations so far today, which have mostly been concerned with getting the hydrocarbons out of the ground. So now I'm going to take you through something that is arguably less glamorous, but very important in terms of social acceptability and environmental sustainability for the industry. So just to let those of you know that regarding our work, I'm talking on behalf of monitoring, as we have set it out for Environment Agency England, but there are other regulators that are involved in the industry as well. There's the Oil and Gas Authority, there's the HSE, and of course there are the mineral planners who sit within the county councils or unitary authorities. So the drivers for environmental monitoring, here's just a run through of some of them. Social responsibility. Monitoring of the oil and gas industry is a key public interest. Communities expect operators to take their monitoring responsibility seriously. And the EA approach is currently set out in our technical guidance, which is available on gov.uk. We can also see, from a legislative point of view, we've got the Infrastructure Act, which came in a couple of years ago, and behind that as well, most of the legislation which comes from Europe has been implemented into the UK domestic legislation through the Environmental Permitting Regulations, the EPR 2016. So there's also practical reasons there. So for groundwater, for example, water supply, and that also feeds into rivers. The groundwater feeds our rivers. So those are all some of the key drivers for environmental monitoring. So what actually makes an effective environmental monitoring regime? So we need clear scientific justification for what we're asking operators to do. Environmental monitoring asks have to link to the real possibility of environmental harm. The aim of operator monitoring is to obtain evidence to improve our understanding of new techniques, environmental impact, and assessing operator performance in relation to discharges. And early shale gas sites are going to almost certainly be expected to carry more of the burden and do more monitoring and therefore sustain a bit more cost than those projects which come later on. This is unfortunate, but it's one of the factors of it being fairly new within England. We've spoken to industry about that, and they are aware of the responsibilities that are on them. So what is the scope that I'm covering here? Well, flares and air quality is one of the biggest of all. The background map of that slide shows the regional context. That's of the north of England, and that's something we're really concerned about, is looking at what the regional cumulative impacts will be. Flares, we are investigating different flare designs and doing a lot of work to make sure that the relevant monitoring is carried out to assess the actual performance of those flares. Leak detection and repair, the lower left-hand shot there is from a FLIR camera, many of you will recognise. And we're aiming to ensure that companies, that operators have proper leak detection and repair schemes in process. Groundwater is a key area, as I've already mentioned, and we will want to make sure that appropriate groundwater monitoring schemes are in place. And of course, seismic activity. This is where the seismic activity could lead to leakage and therefore environmental pollution, as separate from the OGA's requirement, which is just looking at seismic events on the whole. So looking back at air quality monitoring, as with all monitoring, baseline is absolutely essential. We just need to know really clearly what the air quality is in that area so that we can see if there's been any impact. Operators are going to generally be responsible for the monitoring on and close to the site. On the regional scale, that's likely to be government taking the lead on that. And we're already working with other partners in order to look carefully at the requirements for that regional monitoring. That's particularly crucial that we get the statistics right on that, because the results just taken on a snapshot can be so variable. So a little bit more about leak detection and repair. So we will be expecting the operator to develop the risk-based monitoring and repair program to an appropriate standard. and then this will be approved by ourselves. Some of the considerations there for guidance that they can follow are listed. So we've done quite a bit of thinking around this already. So looking at groundwater, these are some of the minimum periods which we would expect operators to monitor groundwater for, generally around 3 to 6 months. There's a big exception in there, which is a requirement of the Infrastructure Act, where hydraulic fracturing is being carried out, and the government has required at least 12 months baseline monitoring, specifically for dissolved methane in groundwater ahead of any activity, any fracturing activity. These timescales obviously will need to be extended if there's any particular issues. So if there's any instability in the groundwater, high seasonal variation, or if they need the data to support a hydrogeological risk assessment. Okay, so how our monitoring requirements are implemented in the permit? This is through the environmental monitoring plans. This is how we get it done, basically. The operator develops an environmental monitoring plan based on the conceptual site model, so that they understand the source pathway receptor linkages that could apply. And that will enable them to actually carry out the relevant risk assessments and make sure that the monitoring points are in the correct location. At the moment, that has to be supplied to us at least 28 days in advance of any activity, but we're looking for the future that we could bring that forward and have that submitted as part of the permit application to try and link it in with the other thinking that is done around the whole activity. So that then forms part of the operator's permit under their operating techniques, and that gives us the tool to make sure that that is actually done and carried out correctly. In those cases where a site falls under the Industrial Emissions Directive, and this is generally where there are flares which are processing more than 10 tonnes of gas per day, then there will perhaps be more additional monitoring requirements, such as for soils. So coming on and looking at how this relates to Europe, the European legislation at the moment. Of course, we don't know what's going on going forward, but at the moment, we have to look at what the BAT requirements are. That stands for Best Available Technique. And Best Available Technique for environmental monitoring is set out there, and we call this the standards hierarchy. The key thing here is that Europe is developing draft hydrocarbon Best Available Technique guidance at the moment. That's not a BREF document, and that work is in progress. There is a mining waste and extractive industry BREF, which obviously only applies to the extractive waste generated on these sites. That is coming to its conclusion. They hope to publish that document, that BREF document, in about May or June next year. And that also